In the previous lectures, we finally introduced the partition function, the instanton partition function, albeit for the simplest gauge theory, which was the function of the instanton counting parameter and a bunch of covariant parameters. And I introduced the so-called Y observable. And so I said that we will be studying correlation functions of, let's say, Y observables and maybe Laurent polynomials built out of them. And so of all possible combinations of y's you can insert, of course you can take sums. I said that there are interesting ones which exhibit interesting analytic properties as far as the dependence on the variable x, one of these variables is concerned. And so today we are going to generalize, we're going to first see that more explicitly. Namely, I will show that the expectation value of the following combination of Y observables. So that's so this combination is entire function in X, and therefore it's a polynomial. So that's the main result. So this particular combination is the simplest example of the QQ character. Are we out of pens, right? Oh, here they are. Okay. So this is the simplest QQ character, although this should be probably called epsilon character, because this is in the realm of cohomology theory. The QQ characters are actually living in K theory, but that's a minor point. So everything I said has a K theoretical analog, and so a Q analog, if you like. And so we will be now generalizing both the types of instanton calculations one can do, and the accordingly the types of the observables one can insert, and the observables which have nice properties. So we will generalize today. I want to generalize that, and we will generalize it to the so-called quiver gauge theories with matter. So this theory was, so the simplest partition function which we studied so far corresponds to the simplest quiver, which has one vertex and no loops, no edges whatsoever, and no matter. And so we will generalize that, and then we will generalize this. So this is, by the way, of all QQ characters, this is also the so-called fundamental one. So the terminology follows the terminology for the ordinary characters of Lie groups or Lie algebras, where you have characters corresponding to fundamental representations, and then you have characters corresponding to general representations or general weights. And so this one corresponds to the fundamental representation of the Lie algebra corresponding to that quiver, which is known as A1, or also known as SO2. And if you look at this expression, you see two terms which are roughly speaking inverse. One is inverse of another. And so this should be compared to the trace of an SL2 matrix in a two-dimensional representation. So this is, morally speaking, should remind you the trace of an SL2C matrix taken in a two-dimensional defining representation. So that's the analogy. And in fact, if you take, if you remove all the deformations, all the parameters, if you set all epsilons to 0, if you forget about Q parameter, then this will be literally the trace of a matrix with eigenvalues y and 1 over y. So that's X variable lives in a complex line. All right. And so today we'll be playing with these characters. We'll mostly for the A-type quivers, but towards the end I will write the general formula for the general quiver. And tomorrow we'll talk about the geometric origin of them, of those, the reason for this analyticity property, and the consequences. So from this we'll derive interesting equations. Yes, that's tomorrow. That's it. The geometric meaning. Yes. All complex lines look alike, but of course some of them are the algebras of a, let's say, multiplicative group. What? No, it's a correct question. So this C is the Lie algebra of the multiplicative group. So it does have a equivalent meaning, but we're not in a position to discuss it yet. So we need some time. Okay. So first of all, I want to generalize this object, and so I will borrow. So the motivation comes from physics, but it has there is also. Okay, maybe I can explain this in a more mathematical way. So let me first do the one generalization, which is to add matter. So let me add. So let me do this, the following procedure: add adjoint matter. So what do I mean by that? Remember, in our paradigm of fields, equations, symmetries, every term in this triad comes with a certain supermultiplet. So we had some multiplets like x psi for fields, we had chi h multiplets for symmetries, for equations, and we had sigma bar eta for symmetries. So the actual expression for the equations is not always that important. What's important is where the equations take values, because that's what determines the type of multiplet you introduce. So the equations which we are solving when dealing with ordinary instantons were the equations involving two square matrices and two rectangular matrices. And then there was the moment map equation, which can be replaced by the stability condition. So now what I want to do, I want to essentially kill all degrees of freedom in my system. So what do I mean by that? You see, the space of solutions to these equations, I should have mentioned that earlier. So this is, as we discussed, this is the, it's actually smooth algebraic variety of positive dimension. So you can calculate the dimension of this space is twice Kn. So it means that if you really want to integrate something over this space, the differential form, which you need to insert here, has to have a positive degree. So the degree of omega should be 4kn. And that's somewhat of a bother because, well, you have to come up with the differential form of the degree. So where do you get it from? You could build it using the polynomials and sigma, but that's there's no canonical choice, let's say, let me put it this way. So it would have been much better if the space which you've defined were of dimension 0, because then integration over that space would be just counting the points or maybe evaluating functions at different points. So, and that's what I mean by killing degrees of freedom. So it is better to maybe impose additional equations, maybe at the expense of introducing additional variables, so that so as to make effectively the dimension of the modular space equal to 0. So we put its effective dimension. In other words, what I want to do, I want to produce, somehow cook up a cotangent bundle over my modular space of instantons and compute its equivariant Euler characteristics. Equivariant in a sense which I will specify in a second. So actually, it turns out that there is a canonical procedure for doing this. This is so-called a co-field construction. So that was introduced by Moore, Stefan Cordes, and Sanjay Rangulam in 1994. And then, well, in the context, they did introduce it in the context of Hurwitz's theory of theory of counting holomorphic maps of Riemann surfaces to Riemann surfaces. And in that context, it was kind of, it was not really recognized as an important universal construction. Moore and Digraph later generalized it to more general theories. But it was, in the context of instantons, it was really made quite explicit by Waffe and Witten in the same year, who recognized that this construction is actually inherent to the twisted version of n equals 4 Superman-Mills theory. So this is the maximally supersymmetric gauge theory, which lives in 4 dimensions. And so while n equals 2 Superman-Mills theory in the twisted version computes Donaldson invariance of 4 manifolds, that theory computes essentially the Euler characteristics of instanton modular spaces. Now, in the work of Waffe and Witten, they were mostly concerned with the study of the theory in compact manifolds. So for them, the Euler characteristics were just numbers, and the beautiful structure which I'm going to explain was not visible there. So we're going to work on R4. And that's where you have all the parameters which I'm going to explore, which make the structure visible. Okay, so to make the long story short, so n equals 4 Superman-Mills differs by n equals 2, from n equals 2 Superman-Mills by additional matter multiplets. And so by analogy, we should expect to introduce more variables to the ADHM construction. And these variables are essentially dead. So you introduce new fields, which are called co-fields, which are dual to both equations and symmetries. And now, in the adjoint construction, we have three Lie algebra valued equations. So my deformation parameter r, I moved into the definition of mu r. And so dual fields would also take values in the k by k matrices. And now the symmetry is the group uk. So the field dual to the symmetry will also be a k by k matrix. So overall, the co-fields will be 4 copies of the Lie algebra of uk, which is equivalent to having 2 extra complex matrices, which I will call B3 and B4. So for the reasons which will be clear later. And so this is my new construction now. I have the space K. I have the space N. Again, I have the operators I and J. And now I have four B's. So in total, I have four matrices, 4 complex matrices, or 8 real matrices, and still 2 rectangular matrices. So now I want to impose as many equations as I have variables. So kill them all. And the way to do this in one kind of swoop is to say that, let me view these 2 complex matrices as a triplet of, so phi hat belongs to the Lie algebra of uk cross R3. And one more matrix, let me call it sigma R. So let me introduce the so-called superpotential, although this is going to be a real function, so it's maybe I shouldn't call it W. So it's going to be kind of a Morse bot function on the space of all my fields. And so this is going to be trace phi vector dot mu vector. So mu vector is the union of these guys. Mu r, real part of mu c, imaginary part of mu c, plus. So the nice thing about R3 is that we have the cross product. What is called for 2 vectors, you can take the vector product and then take a scalar product with the third vector. So the interesting function which you can have here is this one. And now I want to impose the equations so now I want to impose as many equations as I have variables. And my equations will have the following structure. The derivative of f with respect to any variable plus the infinitesimal gauge transformation, so uk transformation generated by sigma r applied to this variable is equal to 0. So for each variable, I impose that equation. And this is, it's almost like imposing looking for critical points of the function. But because I have a symmetry in the problem, I'm allowing for generalized critical points, which are, so the function is stationary up to the symmetry transformation.
Can't you change f by adding more terms? So
Well, that's, I mean, I could just forget about this term. It's just the equations will look less nice.
There's a way of writing the action as a gradient integral. Is that possible?
No, this is not the action. The action is actually the square.
Action, I meant the
Potential?
No, the delta sigma.
Oh.
Not action as in physics, action as in geometry.
No, but there's some, in fact, in some sense there is an I in front of it. So this is not a gradient. That's what it's really the. All right. So what I want. So the point is that there are as many equations as there are variables, and these equations are sufficiently generic. So why, for example, why is not good? Why do I need to have add this correction term? So why resist Ezra's suggestion? Because when your equations have this form, these equations are always dependent. Because you can take the derivative of the function with respect to one variable and then another variable, and that's the same thing as take a derivative function with respect in other order. And we want to impose equations which are sufficiently transverse. So that's why I really need to screw this up. But it is convenient to have a potential because that makes sure that you have as many equations as you have variables. All right, so.
Four matrices, right? And B1, B2, B3, B4.
So, no, B3 and B4. So if you like B3 dagger and B4 dagger. This is the new stuff. And variables involve old stuff and new stuff. Okay, so when you open this all up, what it becomes, so the equations which we had before, namely mu c equals to 0, gets replaced by this equation, mu r requires eventually this correction. In addition, B3i plus B4 dagger, J dagger is equal to 0. B4i minus B3 dagger, J dagger is equal to 0. And finally, commutator of B1 with B3 plus commutator of B4 B2 dagger is equal to 0. Commutator B1 B4 minus well, plus, so it's a cyclic thing. So if you count the number of square equations, here are 2, because these are complex equations. 1, 3, 2 plus 2, 7 plus, so all in all we have 7. So 7 UK valued equations plus symmetry. So we still have a compact symmetry, modulo UK. And then these equations are rectangular. So they take values also in the maps between n and k. And so they impose as many equations as you have variables in I and j matrices. So overall, the number of variables and number of equations are equal. Now, when you actually try to solve these equations, you will discover very soon that these equations imply that B3 equals B4 equals 0, and we are back at the modular space of instantons. Because once B3 and B4 equal, say it again? No, they are not transfers. So so you want them to be sufficiently transfers, but they are not transfers. And but the point is that we now have, so we have the multiplet of the addition, we have additional chi-h multiplets, which which are responsible for the additional equations. And so what they will produce, they will produce in the integration measure over the space of solutions of these equations, which is the old modular space. They will produce the representative of the Euler class of the cotangent bundle to the modular space of instantons. Now, yes. No, this is not the Kajima variety. It's something new.
I know well, I was sort of asking, in principle, before if I did this from like the
So all this corresponds to the following picture. If that's what you're asking.
Right, but you sort of took twice as many loops now, right? That's supposed to be the conclusion that we did the same for, right? Different equations, different.
So we're integrating. We're now integrating something sensible over the old variety. In the past, you had a variety of positive dimensions, so you had to, if you wanted to produce a number, let's say, you had to come up with a cohomology class or K-theory class to integrate over the space. I'm telling you that there is a geometric construction of a certain class which simply comes from taking a different space of virtual dimension 0, which projects onto this Nakajima, to the old modular space, which happens to be a Nakajima variety for that quiver. And so by taking the class, the unit, just one, and taking its push forward in equivalent cohomology, will produce an interesting class which you can integrate over that variety. This is not a quiver variety. It's not a quiver variety. You see, no, it's not, because you see, well, I don't know what your definition of quiver variety is. Do you see all daggers here? So my equations are not complex analytic. Well, in the sense that there are dots and arrows, and on the blackboard, everything is a quiver variety. Maybe so. Okay. Maybe so the procedure which I described can be applied to any quiver variety. So any quiver variety, you can run certain machinery and produce the analog of this. I will not call it doubling. It will not always be doubling of the set of fields, but it will enhance the space of homes corresponding to various arrows in different ways. Sometimes in this enhancement procedure, you will get maps between, framing. The framing space may actually start mapping to a vertex which is not attached to that, which does not correspond to that framing vertex. So here it's everything. So here there's only one vertex, so there's not many places to go to. But once we generalize to other quivers, it will show up. Well, this equivalent gradient equation was pretty geometric, actually. I'm not sure I follow. So, in some sense, this is a kind of a basic space from which we can get everything else by applying the orbifold cross product constructions. So this is a kind of a mother of all other examples, and if you understand that, then you understand everything else. Or the father, I don't know. Okay, so one interesting feature of that construction is that even though set theoretically with the space which you're producing is the old space, but the equations and the variables which we introduce have additional symmetries which we haven't had before. So new symmetry So the symmetry will involve, obviously, the rotations of B3 and B4. So there's an SU2 group. And there is another group. There is a U1. So an SU2 just rotates B3 and B4 among themselves, just like we had an SU2 yesterday, which was rotating B1 and B2. And U1, what we call chi symmetry. So it sends B1, B2, B3. That's actually the old symmetry. So it maps, it multiplies B1 and B2 by the face, and B3, B4 by the opposite face. So you can see that this correlation between the phases is needed for these equations to be invariant.
And also I, or is it J?
And also J. Correct. So also, thank you. So J, I, J, I, e to the 2 I chi J. So this term here, for example, so before J will be multiplied by e to the I chi before J. So you have twice from J and minus from before, and then it will be the Hermitian conjugation will flip that face, and that's the same face you get from B3. So that's all consistent. And then the SU2 will act linearly on these equations, and the conjugation minus sign are important so that it's all consistent. So now that we have additional symmetry, we've earned an additional parameter in our. Okay. Believe me, I spent not a single sleepless night verifying that all this works, even though this should be trivial in some sense. All right, so new parameters. So new symmetries, new parameters. It's so important, so I will write it in big letters. So new equivariant parameters, actually just one parameter, but I like to call it 2 and impose a constraint. So in total, we'll have 4 epsilon letters, epsilon 1, epsilon 2, epsilon 3, epsilon 4, and the condition is that the sum is equal to 0. So the geometric origin of this construction in string theory is that that theory which I'm discussing, for which this is a modular space, is this theory which lives on a stack of the so-called D3 branes. So D3 branes in type 2B string theory. So these branes span an R4 sitting inside a 10-dimensional space. So there is a transverse 6-dimensional space of which, so this transverse R4 cross transverse R2. So don't ask me how, but this R2 represents the sigma field, which takes care of the gauge symmetry. And so this is where the eigenvalues of the sigma matrices take values. And so the remaining 4 dimensions are represented by the matrices B3 and B4. So B1, and B2 are kind of non-commutative versions of the complex coordinates along the space of the theory, and B3 and B4 represent the would-be motion in the transverse directions. And so the reason why we get that solution is that the brains don't like to move in transverse direction, or rather instantons, which are attached to the brains, and they don't like to go out in the directions. And now these parameters, they correspond to symmetries which are left unbroken by the presence of the brain and which are constrained by the supersymmetry. And so the symmetry of this picture, when things are properly analyzed, is the product of so there is one SU2 subgroup of the rotation group acting along the brain. There is one SU2 subgroup of the rotation group acting or in the orthogonal space to the brain, and then there is a U1, which is a common which is a maximal torus of the SU2, which is a diagonal SU2 in the product of the remaining two SU2s in the rotation groups. So that's in SU2 diagonal, which is in SU2 1 2 prime cross SU2 3 4 prime. So I remind you that spin 4, the spin cover of the rotation group in 4 dimensions, is a product of two SU2 groups. So one which preserves complex structure, in arbitrary complex structure, and the one which rotates complex structures. So the ones which preserved are explicit, we see them explicitly, and the ones which rotate complex structure, they're broken down to the U1 subgroup, which is this one. All right. Yes. Okay, so I claim now that if you run my machinery of computing integrals by localization at the fixed points, the fixed points of the global symmetry group are the same, because we already have B3 and B4 equals to 0 just by solving these equations. By the way, it is not difficult to prove that. It's you just well, if you don't know, by tomorrow I'll explain, but I'll leave it as an exercise. I forgot to add it as an exercise to my set of exercises today. And then for B1, B2, I, and J, we have the yesterday's analysis. So we again have the summation of the Young diagrams, but now we have new parameters, and they should show up somehow. And so my partition function will now be the sum over the n-tuples of partitions. Q to the total size. And now we get the product of the type we had yesterday, where now instead of the denominator we'll also have a numerator, which I will write in this form. Now e to the wj is, remember, is this object. Compared to yesterday, I now specify explicitly the lambda dependence. Where k lambda is the character of my partitions. Now, you might be surprised that, you see, in this presentation, the role of B3 and B4 was completely symmetric. So my parameters epsilon 3 and epsilon 4 should be on equal footing. And actually they are. So they, even though the way I wrote it here, it's not obvious, but you can actually, so if you call this T, so T has the following obvious property, which reflects the symplectic structure of Q varieties, and in particular the instanton moduli space. So the conjugate of that character, if I take a conjugation and multiply by Q1, Q2, I get the same thing. So that's the symplectic nature of my space. So it means, now at the level of these weights, it means that the set of weights is invariant under the following procedure. You take a weight, some kind of reflection. So it's a shifted reflection. You shift it, you replace it by epsilon 1 plus epsilon 2 minus itself. And so this product is equal to, therefore, epsilon 1 plus epsilon 2 plus epsilon 3 minus wj. So I applied the symmetry to the numerator. And then this is equal to, by that relation, this is, by the way, called the Calabi-Yau condition. In physics jargon. So then this is equal to the product of epsilon 4 plus wj over wj. The number, so there's a -1 here, but the total number of terms is even. So this j runs from 1 to twice nk. Remember, this was the dimension of the modular space, so the total number of terms here is even. Therefore, this sign doesn't matter. So it means, so that's why you can put here whatever you want, epsilon 3 or epsilon 4, doesn't matter. The same product, you get the same product. So there is a symmetry which this structure should have. Now, this parameter epsilon 3 is sometimes called a mass. It's the mass of adjoint hypermultiplet, big name for a small parameter, or adjoint mass for short. We can recover the partition function of the old theory, the one which we studied yesterday, by taking a limit when epsilon 3 goes to infinity and q goes to 0. So old so we get pure theory by taking the limit epsilon 3 goes to infinity, q goes to 0, such that the product q times epsilon 3 to the power n, let me call it q alt, is fixed. Maybe 2n. Yes. So in that limit, only the leading term in epsilon 3 expansion survives, and so the numerator effectively becomes a constant, which is what we had yesterday. So if you can analyze this theory, you can analyze the old theory as well. So that's the advantage. Okay, now once I have that theory under control, we can do a lot of generalizations. And that's because yes.
So the ones with epsilon 3 went to 0, that fraction is just 1, is something special happening?
Yes, if epsilon 3 is, what would you say to 0?
If epsilon 3 goes to 0,
Yes. If epsilon 3 goes to 0, then this is just 1. And this partition function you can trivially compute. in your head.
And why is, like, what does that correspond to? Like, actual or something?
That means that you are computing the ordinary order characteristics of the module space of instantons, which by the usual fixed point analysis is just the number of fixed points, because this is a complex manifold, and the fixed points are antiples of partitions. So you're just counting the number of partitions, and then Euler did it for you, except that you need to raise it to the power n, little n. And so what you find, trivially, is that this is essentially modular form up to some trivial prefactor. And that's the first test of the famous symmetry called S-duality. So the symmetry which acts on the parameter q in a complicated way. So q, if you write q as exponential of 2 pi square root minus 1 tau, then the symmetry acts by sending tau to minus 1 over tau. It is not obvious that the theory has any invariance or covariance properties under this symmetry, but it does. And that's a test. That's a way to test it. So. Yes. Yes. And n of them, little n.
The epsilon 3 parameter came from the transverse limit background?
Yeah.
And the space you're computing in terms of that, it's what? It's like D0, D3 balancing or something?
D minus 1.
D minus 1?
Yes. Yes. So this integral which we are computing is it's a limit of the Witten index of quantum mechanics of D0 branes bound to a D4 brane, and in a dual picture that becomes the integral of the positions of the minus 1 instantons, which is what these matrices are. Very good. Okay, so yes. But we're integrating a different thing. We're now integrating a different thing. Yes, so the extra symmetry, it doesn't act, so this extra symmetry doesn't act on the space, but it acts on the, it doesn't act on the visible space, but it acts on the odd part of that space, which we don't see as actual parameters. So it acts on fermions. And so in practice, what it means that, well, I might as well just write it. So this partition function, it computes, so it's a sum over the instanton charges, q to the k. And then you integrate over the module space of instantons. And now you compute, you integrate the Chern polynomial. So this is Chern polynomial of the tangent or cotangent, doesn't really matter, bundle of the space evaluated at epsilon 3 or epsilon 4 for that matter. So it is really a polynomial at epsilon 3, and you see it is a polynomial. So it's a sum epsilon 3 to some power, and then the Chern class of rank 2nk minus L. So this is what you're integrating. That's where this parameter is entering. Okay. So now we want to. So we have two things to do. So we can try to now explore the Y observables and try to define qqcharacters for that theory. And maybe that's what we should do first. And second, we can generalize this theory to yet more general class of theories, which will be parameterized by quivers. And so from that, we'll arrive at qqcharacters corresponding to general quivers. Well, in the way I will present it, these will be ADE type quivers. but then you can generalize it for even more general quivers. Okay, so let's just let's first stay with this theory and do a calculation involving the y observables. So we will be using the same y observables, which I will write in the Plutistic form. So it's e to the x s star. So if s has the same form as before. Well, this observable, whose evaluation at a specific fixed point is given by this formula. I guess I should put minus to be in agreement with this notation. Say it again? Well, because I said so. This is my notation, and this will be our building block. Out of that, we'll build something new. The Q character will be different, but this is just a canonical object we can associate to our theory. So remember, this is this observable. It's a rational function whose poles correspond to things you can remove, and zeros correspond to things you can add. So for the Young diagram, for the individual term in the for one of the Young diagrams, things which you can add are the upward corners. So these are delta plus, and things you can remove are the inward corners. This is delta minus. So now I want to play the following game. So I want to find out how does this measure, let me call it measure, how does the weight of the particular antipole of partitions, Young diagrams, changes, how does it change when I do precisely that, when I add or remove one of the boxes. So let's compare So let's do the comparison of, so suppose we have lambda and then lambda prime, which is obtained from lambda alpha by adding, let's say, one box. And remember, what you can add should be in the, my color is not consistent. So what I can add is in the delta plus of lambda alpha. So is it clear what I'm doing? So I'm adding a specific one of these boxes, one of the squares. And that defines a new partition. So what I want to compare the characters of the tangent spaces. Now notice that the character of the tangent space is a so it's a, how to say it? It's a sesquilinear form in the character of the partition. So the character of the partition changes in a simple form. We simply, so k is simply shifted by the content of the corresponding square, well, and also taking into account the color to which it happened. So t sub lambda prime, therefore, will change so these terms come from the from the first part of the tangent character. And then from the quadratic part, you'll get, well, you should get 3 terms, right? Because so k is shifted by 1 term. And when you open brackets, you'll get cross terms and the last term. So the cross terms will effectively replace n by s. And this n by s star. And then you get minus p12. So that's the last term. So this is when the content of the new added box is multiplied by its conjugate, which gives 1. Right? So naively, now that since this guy is a platistic exponent of T lambda times 1 minus epsilon 3, my measure, my weight, now when I pass from lambda to lambda prime, using the using the fact that this platistic exponent sends sums to products and differences to ratios. So what's additive here will become multiplicative here. So it will be E of T lambda P3. And now we use this definition. So I'll get something like 1 over y evaluated at lambda, evaluated at a alpha plus c square plus epsilon 1 plus epsilon 2, evaluated at lambda, and here I get the same thing shifted by epsilon 3. And here I have S, so now the identity which we need to remember about this platistic exponents is that if the sign in exponent is changed, then the whole thing changes sign. And so I can conjugate inside and map this to y of a alpha plus c, y of a alpha plus c minus epsilon 3. And then there is a nasty term, which is E of P12, which is P123. So it's 1 minus Q1, 1 minus Q2, 1 minus Q3. So the bad thing about it, minus, is that it contains, so when you open the brackets, you'll get something like minus 1 plus Q1 plus Q2 plus Q3 minus Q1 Q2 minus Q1 Q3 minus Q2 Q3 plus Q1 Q2 Q3. And the bad term is minus 1 here, because by my rules, e to the e of minus 1 is e of minus e to the 0, which is 0. So naively, it looks like what I've computed makes no sense because it seems that the whole thing should vanish because it contains 0 in the numerator. Fortunately, it also contains a 0 in denominator because I'm evaluating, or maybe the other way around. So I'm substituting into the y variable evaluated at lambda the content of the box which can be added. And I mean, the shifts are precisely the correct ones. And so one of these y's in denominator actually vanishes. And so what happens is that, so you get 0 over 0, but the zeros actually exactly cancel. And so you should read this formula in the following way. So you remove, so you actually evaluate, okay, let me say it slowly. So this formula, after canceling zero over 0, reads as follows. It reads as the residue of y function at the argument shifted by epsilon 1 plus epsilon 2 plus q times y of x minus epsilon 3 y of x plus epsilon 1 plus epsilon 2 plus epsilon 3, and here divided by y of x. So the residue at x equals a alpha plus the content of the box, which you can add to lambda, is equal to 0. So here I'm evaluating this at lambda prime. And here I'm evaluating this at lambda. Okay.
So this is a relation of each one.
So once again, so let's take the y function, evaluate it. So take y function, evaluate it at lambda prime. So y function at lambda prime. And here I'm still using a generic x. So x is generic. So this is as before. So this is a product over alpha, and then product over boxes in D plus of lambda alpha prime. Well, sorry, alpha is a bad now. So product over beta from 1 to n. It's lambda prime beta x plus epsilon 1 plus epsilon 2 minus a sub beta minus c of the box. Let's call it box delta box tilde divided by delta minus x minus a sub beta c. These things. Now, so this expression has many poles, but one of the poles we know because that's the pole when beta is equal to alpha, and this box tilde is equal to the box which we added to lambda to make it lambda prime. So this is lambda. And so this is the box. So this box belongs to lambda prime alpha, but does not belong to lambda alpha. And so now I want to take the residue of this expression. So it has a pole at x equals a sub alpha plus c, the content of that specific box. So the pole. So what is the residue of this pole? You just cross this precise factor corresponding to that pole, and substitute x to be equal to that in everywhere else. And that will take care of part of this, most of that product. Now, in my formula, it is in denominator, but I'm multiplying, so I insert this, I will insert it in the partition function, so this y will actually multiply this measure factor, and so that part will cross out. And so what you will be left with will be 2 y's in numerator and 1 y in denominator. And I claim that that will be exactly cancelled by the residue of a different term in the partition function, where now you take y function evaluated at lambda. So it's smaller partition, not lambda prime, at lambda. So that expression will have, among other things, it will have a pole at the 0 of the y function. And the 0 of the y function at lambda contains the content of that very box, because for lambda it can be added. And so this manipulation will show that that residue, without this q factor, the residue will be exactly the missing factors in the ratio of 2 instanton measures. So when you glue everything together, you'll get the precise cancellation of the residues. So that's the beginning of the procedure, which you should think of a kind of a Q analog of the procedure of making a Weyl invariant function where you generate the Weyl group by simple reflections, by reflections at simple roots. So what I did, okay, let's do it slowly. So what we found is that if I take y of x plus epsilon 1 plus epsilon 2 and add it to it, this thing, then I cancelled, so I've cancelled, so this guy has no poles coming from zeros of y of x or the poles of this thing. It has new poles now, because now I have new y's in the numerator, and so I will need to cancel them by adding new terms. So in order to cancel this guy, we'll add the term q squared, and so we'll shift. So we need to shift by, so the argument of this y's is negative, is plus epsilon 4, if you like. So we'll get and this is plus epsilon 3, so y of x. And that cancels y of x in the denominator. So that's, now this guy is this shifted by epsilon 1, epsilon 2. And then I have y of x minus epsilon 4. So now that guy takes care of the poles coming from the poles of this guy, of this factor. This factor still produces new poles, so we'll cancel them as well. And so when you look carefully at what you're getting, you're actually building again the Young graph. So this corresponds to the empty set. This corresponds to the partition having one box. This corresponds to the partition having two boxes, and then you can have these things, and so on and so forth. So eventually, this whole series becomes the sum over a single partition, and there is a prefactor which you will be getting. So product over the boxes in the partition. Okay, let me write it as a S function. Where I now have a new notation for the content of a box. So sigma of a box is now epsilon 3 times I minus 1 plus epsilon 4 times j minus 1. And the S function is x plus epsilon 1 times x plus epsilon 2 divided by x plus epsilon 1 plus epsilon 2. And finally, arm and leg are lambda I minus j and lambda j transpose minus I. These are familiar concepts from the theory of Jack polynomials. So arm is the number of boxes to the right, and leg is the number of boxes strictly below.
Sorry, in terms of reading the argument of this F, can you say that?
Yeah, yeah. So let me just say. So it's epsilon 3 times the leg of the box plus 1 minus epsilon 4 times the arm of the box. And if I didn't make a mistake, so this formula, this product has a symmetry in which you exchange epsilon 3 and epsilon 4. And transpose the partition. Yes?
Just finish, please.
Yes, yes. So of course, once you found this formula, you start filling it. And so when you fill it, you understand that this formula is actually an integral over a familiar by now space, which is the Hilbert scheme of points on C2. And so that's the origin of the whole theory. So the point is that now, so this formula, even though we were doing some calculation of a modular spaces of instantons, which we're leaving on the horizontal R4 with coordinates 1 and 2, z1 and z2 with parameters epsilon 1 and epsilon 2, this formula feels like a formula which is obtained by integrating something over the space with coordinates z3 and z4, or b3 and b4. Because the contents now of the boxes in that formula, this auxiliary formula, are weighted with weights epsilon 3 and epsilon 4. So something interesting is going on here. And we will build the geometry behind this tomorrow. But, yes? Yes.
So, Dylan asked what happened when epsilon 3 goes to 0 and you got some eta functions in modular form. Is this integral with epsilon 3 turned on in some sense a modular form? And are these?
In some sense.
Okay.
Yes. So it's a quasi-modular form. So you can expand. And okay.
And does this multiple Q zeta have to talk to this y observable story? Like is this story?
Yes, yes, of course, yes, of course. It's, I mean, it's all okay. But quasi-modular, it's maybe I'm misusing a technical term, but all of these, of course, these are some matrix elements in representation theory in representations of some infinite-dimensional algebras, and Q couples to the Virasoro generator L0, and so there is always modular. So this can be written as a trace of Q to L0, some huge vertex operator in representation theory of some W algebra. And so you can always expect modular covariance, at least because that's this black expression. So this is equal to the QQ character of A0 hat. So this is, okay, it's just a definition. So I'm defining a guy that we call chi of x with the label 1, 0. The label doesn't say anything for the moment, but I'm just defining a new class, new observable, which I can insert in my integrals. And the claim about this observable will be that its expectation value has no poles in x. So all poles cancel.
So is QQ character, is it actually a character or some representation of some algebra?
Yes. Yes. Okay, so let me keep this formula. Let me make the statement here. So chi, the main theorem about chi, has no poles in x. Under the sign of expectation value. So this is 1 over z, and then the same sum, where now we insert this class under the sign of the integral. So Chern polynomial of tangent bundle evaluated at epsilon 3. Now, I should say that since my expression for chi contains powers of q, so when we should re-expand this, and so I should write it as a double sum and integrate over the modular space of so here, so the term chi L 1, 0 of x is the sum over all partitions of size L, and then the same thing. So it's a product of S functions and product of y over y, as before. Okay, so now generalizations.
Is x but
Just a notation. Just a notation. So 1 here stands, so it's, in order to understand this notation, I need to present a generalization. So that's why you can't understand. All right, so the generalization. Generalization take a subgroup, find a subgroup of SU2. So this subgroup defines a graph whose vertices correspond are the irreducible representations. And then you study how these representations decompose under taking the tensor product with the two-dimensional representation of SU2, defining representation. And so you connect the vertices I and j with as many arrows as you have the multiplicity of the corresponding representation appearing in the decomposition. So that way you build the graph. The graph has a, you can assign to the vertices of the graph the dimensions of the representations. So if AI is a dimension of Ri, then from this relation obviously follows that twice AI is the sum so A is the incidence matrix. I can call it just I, so incidence matrix. And that's an equation which happens to play an important role in physics in the following context. So let's take the same graph and now build the following gauge theoretic problem. So we'll set the space Ni at each vertex of this graph and set the space Ki. So we'll do the usual ADHM construction at each vertex. And now if this if the vertices of the graph are connected, then we'll introduce the so-called sorry. Let me just say it in words first. So we can build gauge theory on R4 with the gauge group, which is a product over the vertices of my graph gamma. So gamma is the graph whose vertices are irreps of capital gamma, and the edges are found from this relation. So this is now we put some numbers and vector spaces of the corresponding dimensions at the vertices. And for the moment, let's not put any restrictions on these numbers. And then, in addition, we add the so-called bifundamental matter multiplets. For each, so which will transform, so it will correspond to the home spaces between Ni and Nj. So what it means is that we will, in addition, study the sections of spin bundles coupled, tensored with these vector bundles over R4 or its compactification. Let's say S4. And we'll be interested in solutions of Dirac equation coupled to the instanton gauge fields in the respective bundles Ni and J. And from that, we'll build a certain class over the modular space of quiver instantons, so which is just a product, set theoretically is just a product of the modular spaces which we already studied. And then we'll sum over all possible instanton charges. And then sum over ki's. with new fugacities at each vertex, and then integrate over the space, integrate this class over the space. So now we have a new theory, new partition function, which will depend not on the one, but on the whole vector of fugacities. The whole vector of equivariant parameters. So A will now be the diagonal matrix of the size Ni. So AI. And epsilon 1, epsilon 2, and possibly epsilon 3 and epsilon 4. So epsilon 3 and epsilon 4 can be introduced. It turns out whenever the corresponding graph which you get is non-simply connected, which means in practice for the so you get it for the A-type gamma. So if gamma is a cyclic group, then the corresponding graph, little gamma, has this form with L vertices. 1, 2, 0, 1, 2, L minus 1. And so in this case, epsilon 3 is present. If gamma is of the D or E type, for which the graph does not have loops, so for example, for the dihedral group which I presented in the first lecture, the graph will have this shape. Then the epsilon 3 dependence can be removed by simple redefinition of parameters. So that gives at first. So this is a new kind of enumerative problem, and so it turns out that this theory is nice when these dimensions and I obey similar equation. So it turns out that you want twice Ni to be equal to the sum over J, Ij, and J. In particular, then this class which I'm talking about will have the degree equal to the dimension of that space. So you again integrating. So you again effectively dealing with the virtual dimension 0 problem, and that actually suggests and explains. In fact, in this case, this construction, you don't need to think of it as of a new construction, but it's a kind of a truncation of the construction which I already presented. And let me now explain in what sense this is a truncation and in what sense this is you already know how to deal with this. So I started at 10 past. Probably, okay, should probably maybe 10 more minutes. Okay, so here is the way to get everything, including this class, from these equations, from something which you already know. So this is called we call it an orbifold, but well, let's just call it an orbifold construction. So remember here, in order to write these equations, we had this structure. We had some space K, we had some space N, we had maps, and we had 4 matrices B. But really, let me just not write them this way. Let me write them kind of as a fat arrow acting from K to K tensor C2, 1, 2, and another flat arrow acting between K and K tensor C2, 3, 4. So I want to combine B1 and B2 into a single operator, and I want to combine B3 and B4 into a single operator. So just for the notational convenience. And remember, I said that the symmetry of my equations was an SU2 cross U1 cross SU2. It means that now if I can actually restrict, I can enforce a certain invariance condition on my matrices and the symmetries by which I divide. I can force them to commute with the action of a certain subgroup of my symmetry group SU2 1, 2 cross U1 cross SU2 3, 4. And there are many choices, but let me just fix gamma as before to be a subgroup of SU2 3, 4. And I want to insist on gamma invariance. So now insist on gamma invariance. What does it mean? It means that, so if I take the, so let G of gamma be an SU2 3, 4 matrix. So it represents for little gamma in capital gamma. So it's a representation. So this is a representation, two-dimensional representation of gamma, which exists by definition. So I want to enforce the following condition, that when I act with G gamma on the vector consisting of B3 and B4, it's the same thing as, so this transformation can be undone by similarity transformation. So by some matrix H of gamma inverse, B3, H of gamma. And I want B1, B2 be invariant. And I also need to impose a similar condition on I and J. So in order to set this whole structure up, I therefore need to provide, in addition to the already given action of gamma, so representation of gamma in SU2, I need to represent my discrete group in the spaces K and M. So I need to fix two homomorphisms. So fix a homomorphism capital H from gamma to UK, and little h from gamma to UN. And so I want all my matrices be invariant under the action of gamma, which is when it is represented using these three homomorphisms. They don't have to come from this position. So it's only gamma is. Yes. So okay. So in particular, so what we want, so remember I was a map from M to K. So what I want capital H of gamma times I equals I times little h of gamma. Okay. And similarly for J, so it's H of gamma inverse equals J capital H of gamma inverse. So here I'm using that gamma is in SU2, so there is no additional phase factor which normally J has. So here we don't see it. We can, in addition, I mean, we don't have to, so gamma actually doesn't have to sit inside SU2, 3, 4. It can be a bigger subgroup. It can be a subgroup of all of these things. So of the whole group. So that will produce other generalizations, but today I will not talk about them. So from that, by just enforcing all these conditions, leads to the following structure. So producing the representation of gamma in UK is the same thing, is to saying that my space K now splits as a direct sum of reducible representations with some multiplicity. So Ki is a multiplicity space for the representation Ri, and similarly for n. And so now my linear algebra data presents as follows. So these conditions, that B1 and B2 commute with capital H, mean that now I have so for every so now if I draw this quiver of gamma, let's say for the cyclic group. So now at each vertex I have a pair Ni Ki, so at 0 K0 and 1 K1 and so on. So Ni Ki. So now I have maps. So this condition means that my maps can only act between the multiplicity spaces corresponding to the same representation. So that's equivariance, gamma equivariance. So I have now the map A, so I little I, J little I. And similarly, I have the maps B1, I, and B2, I. But for B3 and B4, these conditions are saying something else. They're saying that the action in the K space should be intertwined with the action with the SU2 action. And so that means that B3 and B4 will be acting along the edges of my K graph. So B3, roughly speaking, so if this is my graph, let me do it. So this is my K graph of gamma without A, right? Then B3, so this is for the A type. So B3 and B4 you can actually write, you can specify who is B3 and who is B4. So B3 will act, let's say, in this direction, and B4 will act in this direction. So B3 goes along the flow, and B4 acts opposite the flow. The direction of flow is your choice. So my K graph doesn't come with the orientation. You can choose it in any way you like. So, so this is what I was talking about earlier. So the equation, so now that we have this quiver version of the theory, we have an ADHM modular space for each vertex. I mean, ADHM data for each vertex. But the equations which we impose now involve, for example, the product B3I takes the framing space for the vertex I and maps it to the framing space, to the K space attached to the vertex which is incident with I. So it's different vertex. And so the Euler class which we'll be building from these equations will now make different vertices talk to each other through these equations. So that's the construction of the quiver moduli space, quiver instanton moduli space, together with the matter bundle over it, whose Euler class will be computing in defining the partition function. So now the Same procedure, painful at first, looking rather painful. Well, so now that you have many k-spaces and you can define many tautological bundles. So you have now the S spaces attached to SIs, the characters SIs. And therefore, you can define Y observables. So now you can ask the tangent space, the tangent character, which is, well, it's a sum over, well, there is a, okay, so how to say this? So what we integrate over, what we integrate in the instanton measure, so this partition function, which is the, so it's a sum over all instanton charges, which are now arbitrary vertex. And now you sum over the fixed points, which will be n I-tuples of partitions attached to every vertex. So now you have a double proliferation of partitions. So I labels vertices, and alpha for a given vertex labels colors from 1 to n sub I. And so now you need to substitute, so compute the instanton measure, which has this platistic form of a platistic exponent. And here you have the difference of two things. So you have the naive tangent space, which is the sum over the vertices of the tangent spaces to the characters of the tangent spaces to the instanton bundles, instanton modular spaces exactly equal to what we computed before. So it's ni times ki star plus q1, q2, ni star ki minus p12 ki I star. So this is the old stuff. And now the analog of q3, the tangent space, which we had before, now that guy should also be projected onto, so from that character, you only keep the character of the gamma invariant part. And so this is the, so that will give you the sum, essentially the sum over the edges. So these are vertices, and these are edges. And you'll get something like n of the target of the edge, k of the source of the h star, plus q1, q2, n star of the source, times k of the target, minus p12, k of the source, star k of the target. So here, for this my k graph, I need to choose some orientation. And once you choose the orientation, each edge has the source. So it's a vertex from which it emanates, and its target, the vertex to which it points. So there are additional parameters which you can insert here, which I will call exponential of ME. So these are called bifundamental masses. And these parameters are essentially absent if the quiver is simply connected, and can be expressed through the single parameter epsilon3 if the quiver has a single loop. So so I will just write it as roughly e to the epsilon3. Okay, so that's the restricted instanton measure. And now if you build, if you now try to repeat the game of finding a correction to yi, so starting with yi at a specific vertex I, add corrections to it. so as to make the expression which has no poles. This way you'll arrive at the quiver version of the QQ character. So the fundamental, still fundamental, QQ character for the quiver gamma. So here my notation is chi I 0, still 0 of x. So it starts as yi of x plus epsilon 1 epsilon 2. This is just something which I like to shift it by. Plus qi. And here it will be a product over all edges which point to I, where you will get y of the source of the corresponding edge shifted by minus by fundamental mass, and then product over all edges which start at I, and here you will get y of the target of the edge x plus epsilon 1 plus epsilon 2 plus me. Plus and so on. So here I forgot to mention that once you generalize, you can also add a new kind of framing to the story, which corresponds to fundamental multiplets. This is, you can get it by taking various limits of this formula. So let me not bother you with those details. So this plus dot 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 can be pretty complicated. It could be, again, an infinite sum. But once you understand how this whole structure is obtained by taking the projection of the gamma invariant subspaces, it's actually possible to derive all of these expressions for the AD type quivers by taking this expression. Well, you need not quite. Well, you need the generalization of the non-fundamental character, which I will explain tomorrow. So this is where the 0 will become non-zero. Eventually, once you get that, you can get any of these characters. So we'll get to that tomorrow. I think I've introduced enough new stuff today. Thank you. Yes, again, of course, the main point about this will be that it has no poles. And it's QQ character. So if you forget about Q, if you forget about X epsilon dependence, it is a character of the ith fundamental representation of Kac-Moody algebra corresponding to gamma. Yes?
So is there by any chance a generalization of this overflow construction for non-simply placed thinking diagrams?
There is a generalization of that, yes. Not at the level of the actual spaces, but so there is, of course, a formula for there is a QQ character for non-simply placed algebras, non-simply placed thinking diagrams, and corresponding algebras. There is some kind of instanton integral construction which I don't quite understand. It's due to Persson and Kimura. So there, you treat the C2, I mean the R4 spaces attached to different nodes differently. So in some you act with, so the rotations act with parameters epsilon 1, epsilon 2, but at some nodes it acts with parameters epsilon 1 and twice epsilon 2, depending on long and short roots. I don't understand, I don't know how to make sense out of it geometrically, but it seems to work. Yes?
Your graphs, do they bring some kind of adjacency graphs of the geometric cycle and surface and operate
Well, it's the old story. So if you remove the vertex corresponding to the trivial representation, then that would be the intersection. Yeah.
Then when you construct your gauge theory, you have that vertex in or not?
Yes, you do have.
You have it in.
Yeah.
So then how do you, like, what's the geometric? What's the string theory construction of this gauge theory?
The string theory construction of that gauge theory, it's what, so you take the picture which I drew before, and then you make an orbifold with respect to group gamma. So you have this AD singularity in the transfer space. Yes.
But it's still in D3. It's not
Just D3. Something, your question reminded me something which I, right. So you see, we have these parameters qi at our disposal, and we can tweak them. For example, we can send some of these parameters to 0, literally, and that will freeze some of the nodes of the Dynkin diagram, of the affine Dynkin diagram. So the gauge group, so the gauge factor at the corresponding node will become a global symmetry group, not a gauge group. And so that way, you can produce theories which correspond to non-affine Dynkin graphs from these theories. And then you can, from that, you can understand what's the fundamental matter, which I mentioned, but I didn't explain what it is. It's what you get by freezing some of the nodes. But I guess, okay, so the point which you should keep in mind is that if you want to get a simple theory, sometimes to get a simple theory corresponding to complicated graph, if you restore it back to, if you go back to the kind of covering space, so the space which you get by collecting all multiplicities, even when your spaces and i's are, let's say, 0 or 1-dimensional, the overall space may have to be at least 2-dimensional for non-A-type groups. So while for the A-type theories you can actually understand pretty much everything in terms of Hilbert scheme of points, which correspond to 1-dimensional ends. If you want to understand non-cyclic, so D or E-type singularities, you need to understand higher rank shifts on C2. So that's something to keep in mind. So that's why this formula, unfortunately, is not always sufficient. But there's a simple generalization of that formula for the non-fundamental characters, which we'll maybe discuss tomorrow. We'll discuss tomorrow.
Does your group X or no, your group X of like B3 and B4 which equals 0?
Yes, of course, B3, B4 being 0 is a possible solution to these equations. Yes. You will appreciate why the role of B3 and B4 once I give you the geometric interpretation of this formula. So in this formula, B3 and B4 are non-zero. Just leave it like that. That's why you need to study them, even though in your previous life they were all zero. Okay.